Hello, lovely grade 12. Welcome back to the channel. In today's lesson, we're going to be looking at electrodynamics. So those AC, DC motors and generators. So without any further ado, let's just get right down to the lesson. So it says in question 9, the diagram below shows a simple model of a DC motor. So here we are told that we are dealing with a DC motor, and we can confirm that because this is connected to a power source. So remember, it is a motor when it is connected to a power source. And then how do we confirm that it is a DC? It's because it has split rings, or rather split ring commutator, right? Then 9.1 says describe the energy change that occurs in DC motor. So what is the energy change in DC motor? Because of this power source, we understand that the motor needs electrical energy, and then it takes this electrical energy and converts it to mechanical energy, which makes this coil to move. So 9.1, it says electrical energy to mechanical energy. Awesome. Then 9.2 says explain the term DC. So what is DC? DC simply means direct current. This is where we have current flowing in one direction only, right? So you will remember that in DC current, this is where you have a graph like this. So it is flowing in only one direction. Then 9.3 says in which direction. So it's asking us in which direction will the conventional current in the coil flow, right? Right, only from P to Q or from Q to P. So having this, we can see that this one here, remember, from our electricity, we know that the longer terminal here represents the positive and the shorter terminal represents the negative. But our rule when it comes to electricity and conventional flow meant to say is that electricity or current will flow from the positive terminal to the negative terminal, right? So that means all this is positive. So your current is flowing like this, and then when it gets here, that means it will flow from Q to P, right? So the answer here is supposed to be 9.3 is from Q to P. Okay, then we have 9.4. It says explain the change that needs to be made for this motor to be an AC motor. So what change must we make in this diagram here to make this an AC motor? So we know the difference between a DC motor and AC motor lies in the use of the split ring when it comes to DC motor, and the split ring and the slip ring mean to say when it comes to the AC motor. So for AC it's slip ring, and for DC is split rings, right? So now note that. So DC is split ring. So it's easy to see for DC because if you can check there, it kind of forms a C and a D shape here. So you can easily see that this is DC motor. Now if we want to change a DC motor to be an AC motor, we simply have to replace this part here by what we call the slip rings, right? So it's replace split rings with slip rings. Then 9.5 says a heater labeled 2000 watts. So here, what are we given? Remember, when we are given like this is the power average power, and then we are also given 220 volts, which this one represents the VRMS, right? The root mean square voltage, and 50 hertz is connected to an AC circuit. Calculate the maximum current that flows through the heater, right? So we must calculate the maximum current that flows through the heater. So what are we going to do with this one? We can see that here the kind of gave us the 50 hertz in order to throw us off, because if you can check here, there is no formula, if you can check in our formula sheet, that requires us to put in the frequency, right? So note how the examiner here was trying to play mind games with you, so you should always note those tricks. Then what are we given here? We are given the power average and the velocity average, right? Meaning that we can use that this formula here. We can use this formula here to find the root mean square current. So by saying P average is equals to V RMS multiplied by R RMS, right? So what is your P average? The P average we are given is 2000. So we substitute in our 2000 here, and then the velocity we've been given to be 220. So now we are looking for the root mean square current, so we can divide both sides by 220 like that, and then our root mean square current is going to be 9.09 amperes, right? Then remember from here, what did they ask us to calculate? They asked us to calculate the maximum current, right? So where do we go from here? We will now use this formula here to calculate the maximum current, where we say I RMS is equals to I max over root 2, right? So we substitute our root mean square current, which is 9.09, and then is equals to I max over root 2. At this point, you know what to do. You just cross multiply this, and then your I max is going to be equal to 12.86 amperes, right? So awesome, that's your answer, and that's your easy peasy 5 marks. In a simple DC generator, so this is a DC generator, the coil is rotated in an anti-clockwise direction as shown, right? As we can see here, this is an anti-clockwise direction. Then 9.1.1 says name the component in this generator that ensures that the induced current in the external circuit is in one direction only, right? So we know that this is a generator, and a generator has a component that we know as the split ring commutator, which its function is one and only to ensure that the induced current in the external circuit is in one direction. So this is the component that we are looking for, the split ring commutator. Then 9.1.2 says is the direction of the induced current from X to Y or from Y to X. Then since this is a generator, we know that we have to apply our Fleming's right hand rule, right, in order to answer that one. But then from here we can almost tell that if this is in an anti-clockwise direction, then we'll have this side facing up, and therefore the current will now flow in this direction, so from Y to X. Then if you want to use your right hand rule, your thumb will indicate the direction of the force, the index finger, the direction of the magnetic field, and the second finger, the direction of the current. And then you'd find that the direction is from Y to X, so the current will flow all the way from Y to the position X, right? So we indicate it by the index finger, by the second finger, meant to say, because it is the direction of the current. Then here we have a maximum voltage of 90 volts is generated when the coil is rotating at a frequency of 20 hertz, right? Then 9.1.3 says write down the time taken for the coil to complete one rotation, right? So at this point we can now use the frequency here, because we'll be using the period formula, which goes big T is equals to 1 over F, right? So period of a wave is equals to 1 over its frequency, so it's 1 over 20, which will give us 0.05 seconds. So it takes 0.05 seconds for one complete wave to form. Then 9.1.4 says the coil starts rotating from the initial position as shown in the diagram above which from this position we know that once it is like this, there is no induced EMF, right? So no induced current when it is just straight like that, because it will be perpendicular to the magnetic field, right? So 9.1.4, it says sketch a graph of output voltage versus time for one complete rotation of the coil. Indicate the maximum voltage and the relevant time values on the graph. So we are told that we must indicate the maximum voltage and the relevant time values. So we know if this is DC, DC only flows in one direction. That means it reaches the peak and comes down, and then again reaches the peak and comes down, right? So assume that the peak here are of the same height, so couldn't draw it nicely. Then they told us that the maximum voltage, output voltage, is 90, so we have our 90 there, but we calculated that to complete this whole cycle, remember this is half a cycle, and then another half a cycle, it forms a full cycle, so it's 0.05. That means we have to find the time in which it takes to complete half a cycle, so it's 0.025. So obviously the last thing to do is just to label your axis. So we have output voltage, which should be indicated in volts, and then here we have time, which should be indicated in seconds, and just like that you would have your 4 marks, right? Okay, so we have 9.2. It says wall socket supply RMS voltage and current. Then they say a 220 volts AC voltage is supplied from a wall socket to an electric kettle having a resistance of 32 ohms. Then it says calculate the average energy dissipated by the kettle in 2 minutes. So let's try to highlight all the data that we have here. We have the 220 volts, which the 220 volts is the VRMS. And then we also have the resistance, which is 32 ohms, and then we have the change in time, which is 2 minutes. We know 2 minutes, we must say multiply that by 60 because we want our time in seconds, so that will give us 120 seconds. Then now what are we looking for? We are looking for the energy, right? So energy is represented as W, the work done, right? So that means for that one we will have to consult our formula sheet and then try to come up with a formula that has everything that we need there. So you can see with this one we don't have the current I, so we're just gonna avoid that one. Also this one we don't have the current, but if we check this one we have everything that we have in our data. We have the voltage in the form of VRMS, and then we have the change in time, which was the 2 minutes converted, and then R, which is the 32 ohms. So we are good to go with which formula? This one, right? So you see how easy it is to just choose the correct formula. Then we have W is equals to V squared RMS times change in time over the resistance. So it's just a matter of substituting here, and then our time is 120, and then our R is 32, and then just punch all that in your calculator. You have 181,500 joules, and just as easy peasy like that, you have your full 4 marks. Okay, so we have question 9. It says a simplified diagram of an electric generator is shown below. When the coil is rotated with a constant speed, an EMF is induced in the coil. So we have our magnet here, and then this is a coil. And then 9.1.1 says, is this an AC generator or a DC generator? So okay, now it is just a matter of us having to check this, if these are split ring commutators or slip ring. So we can see that this is a split ring because of its living spaces in between here. So these are split ring commutator, so that means this is a DC generator. Then 9.1.2 says briefly explain how an EMF is generated in the coil when the coil is rotated by referring to the principle of electromagnetic induction. So easy peasy, that one we just say EMF is induced as a result of the magnetic flux linkage with the conductor. So you will remember this from grade 11, Faraday's law, whereby we had this formula. So we know that an EMF is induced as a result of the magnetic flux linkage with the conductor. Then 9.1.3 says draw a sketch graph of the output voltage versus time for this generator. Show one complete cycle. So we already know the drill with this one. So what are we supposed to indicate is just a sketch, right? No values required. So with the sketch, we know that it goes like this. So because DC has only one direction, so the peaks here are of the same height, then here you just have to indicate this is time in seconds and this is your output voltage, right, in volts, of course. Then just like that, you have your sketch, 2 marks. Then 9.2 says a 200 ohm resistor is connected to a DC voltage supply as shown in the diagram A. The energy dissipated in the resistor in 10 seconds is 500 joules. So we are given the energy W, and we are also given change in time 10 seconds, and we are given the resistance. So that's how we collect the data. The same resistor is now connected in an AC source, so diagram B, and 500 joules of energy is also dissipated in the resistor in 10 seconds. So the difference is here they put it in DC source, and now here they put it in AC source, right? Then 9.2.1 says define the term RMS voltage of an AC source. So this is how we are required to define it. We say the RMS of an AC is the DC voltage which dissipates the same amount of energy as AC potential difference. So this is how you are required to define this according to your CAPS document. Then 9.2.2 says calculate the maximum or the peak voltage of the AC source. So we are required here to calculate the Vmax. But then let's recap on our formulas and also the data that we have. So on the side here, let's write the data that we have. We are given the work done or the energy, which is 500 joules, and then we have change in time, which is 10 seconds. And then what else are we given? We were given a resistance. Is it resistance? So what else are we given here? Resistance of 200 watts. Yes, so we have resistance of 200 ohms, meant to say not watts, 200 ohms, right? So resistance of 200 ohms. Then let's see what formula are we supposed to choose for this one. We are to calculate the maximum peak voltage. So that means in order to calculate the maximum peak voltage, obviously first we'll have to find the voltage, right? So what formula would be best to use in this case? Because we have the energy, we would use this one. We have energy, we have resistance, we have change in time, and we are looking for VRMS. Then from our VRMS we can calculate the Vmax using which formula? Using this formula now, right, which goes VRMS is equal to Vmax over root 2. So now let's go ahead with answering that question. So we have W is equal to V squared RMS, remember, and then times change in time over R. Then what is our W is 500, and then the VRMS is what we are looking for. And then what is our change in time? So we are given it was 10 seconds, and then the R here is 200, right? So at this point we just want to cross multiply this. So we have V squared RMS is equal to this times that, this will give us 10. So it's 10,000. So yeah, and then now we have to square both sides for the VRMS, and then we will have 100, right? So it's 100 volts. Then to calculate the Vmax, we now go to the second formula. It's VRMS is equals to Vmax over root 2. Then at this point here, we just substitute our VRMS, and then we have Vmax over root 2. Then cross multiply here, we have Vmax is equals to 141.42 volts, and just like that you have your 5 marks. Easy peasy. Question 9, it says 41.42 volts, and just like that you have your 5 marks. Easy peasy. Question 9, it says a simplified diagram of an electric machine is shown below. Then we can see that this machine, what is it? It is connected to a power source. At least we know that, so we know this is a motor. And then now they're asking us, is this machine a DC motor or a DC generator? So obviously this is a DC motor because it is connected to an external power supply. Then 9.1.2 says write down the energy conversion that takes place while the machine is in operation. So we know with a motor does what? It takes electrical energy and converts it to mechanical energy, contrary to what a generator does. Then 9.1.3 says write down the name of component A in the diagram. So what is component A? We already know it is what we call the split rings or the split ring commutator. Then 9.1.4 says in which direction will the coil shown in the diagram above rotate? Choose from clockwise or anti-clockwise. So from this we already know if it's connected to a power supply like this, we know that the conversion current will now flow from the positive terminal to the negative terminal. So there is your current flowing like that. And then now we already have the direction of the current, and since this is a motor, we know that the rule that we have to apply is left hand rule. So using the left hand rule to find the direction, whether it is clockwise or anti-clockwise, if you use your direction, if you use your right hand rule, you would obviously find that it will move in an anti-clockwise direction. So I did not get a nice diagram here, but then the current was supposed to face in that direction, and then your magnetic field obviously in that direction. Then what the direction of the direction now will be in that anti-clockwise direction like that. So you can almost see the direction if you just kind of imagine this hand rotating here. So it will rotate in an anti-clockwise direction. Okay, so we have 9.2. It says an electrical device is marked 200 watts and 220 volts. So what does the 200 watts here represent? It represents the power average, and then the 220 watts represents the root mean square voltage, right? So remember, if you are given an electrical device cannot use the maximum voltage. So always know that if they're giving you the markings of an electrical device, then the voltage will represent the VRMS, and the power will represent the average power. And if there is current, the current will represent the IRMS, or the root mean square current. Then, okay, 9.2.1 says define the term RMS voltage. We say RMS voltage is the AC voltage that dissipates the same amount of energy or power as the DC potential difference. Then 9.2.2 says calculate the resistance of the device. So we are given the 220 volts VRMS, and then we are also given the 200 watts average power. So now let's consult our formula sheet. Given that the VRMS is 220 volts and then the power average is 200 watts, we are looking for what? We are looking for resistance. So what formula can we use for this one? If looking at this one, you can see that this one is a perfect formula. We have the power here, we have the voltage, and then we can just use it to calculate the resistance. So we go power average is equals to V RMS square over R, right? Then what is our power average? Is 200, and then here we have 220. You square that, and then over R. Then we know it's just a matter of cross multiplying here. Then 220 square over 200. This will give us 242 ohms, right? If you punch your calculator, then you have yourself a good 3 marks like that. Then okay, it says now the device is now connected to a 150 volt AC source. So now what are we given there? We are given another root mean square voltage, right, in the AC. So it's 150 volts, right? And then remember, this still has the same resistance of 242 ohms, right, because it is still the same device. Then they say calculate the energy dissipated by the device in 10 minutes. What is 10 minutes? 10 minutes is change in time, but then we know that our time should always be in seconds. So what do we do to the 10 minutes? We say 10 multiplied by 60, because 1 minute is 60 seconds. So how many seconds are there in 10 minutes? We do like that and we find that it's 60 seconds. So just like that, we have our data, we have resistance, we have a voltage VRMS, and then we have change in time. And then what are we looking for? We are looking for W, right, which is the energy dissipated. Energy, remember, is work done, right? And then what formula we are looking for? That one formula that we will have all this. So we are looking for energy, but then we have VRMS, which is in this case now is 150 volts, and then we have our R, still 242 ohms, and then we have change in time is 600 seconds. So what formula can we use that will enable us to use this data that we have here? Checking here, we can see that the formula that will be best for this calculation is this one, right, because it is everything that we have there. Then it's W is equals to V squared RMS, multiply that by change in time over the resistance. So let's just substitute. So here we have, so you just substitute that 150, then square, and then here we have 600, and then what is our resistance is 242. Then it's just a matter of punching all this in your calculator. So you have a 55,785.12 joules.